Hydrogen is one of the cornerstones of our future energy needs. It is the most common element in the universe, has more useful energy per pound than any other non-nuclear fuel, and is environmentally friendly. So why has adoption of hydrogen as a fuel been so difficult?
Per liter or per gallon, it's reversed. It's about 1/3 to 1/4 the density of common fuels like gasoline. You need a tank that's about the size of your car.
To increase the density, hydrogen is stored at very high pressures or very low temperatures, neither of which are very practical.
We want a form of hydrogen that will be both dense, you can fit it in a small bottle, and that bottle can be at room temperature and atmospheric pressure.
At the Air Force Academy in Colorado Springs, Dr. John Wilkes has created such a technology using a class of stable solids called chemical hydrides.
It's lithium aluminum tetrahydride.
When reacted with ammonia at room temperature and normal pressures, it releases hydrogen gas.
This is the way we create the hydrogen with this technology. The ammonia comes through the bottom and into the reactor where the hydrogen is formed. The hydrogen then exits through this tubing into this water column where you'll see it bubbling to be collected.
Using this process, the Air Force Academy, in conjunction with industry partners, have created a portable hydrogen fuel generator capable of powering a laptop computer for 20 hours.
This is an ammonia tank. This is a chemical hydride canister. When these two are coupled, it becomes a hydrogen source. Hydrogen comes out here, goes to a fuel cell, and a hydrogen source plus a fuel cell is the equivalent of an electric battery.
What's happening is we're keeping one canister of liquid ammonia that has a vapor of ammonia above it. And it's separated from another cylinder of the hydride. What we have separating those is a check valve. A check valve is just a spring with a ball on the end of that spring. And when the pressure is high on one side of this check valve, the gas goes from the high pressure side to the low pressure side. It's allowed to go. However, it cannot go in the opposite direction. Since there's a low pressure on the canister side and a high pressure on the ammonia side, the ammonia goes into the canister. Reaction takes place, and if that hydrogen that's formed during that reaction doesn't have some place to go, pressure builds up. That pressure closes the check valve and the thing goes to sleep for a minute, an hour, a day, a month, a year, or a decade until you release that hydrogen pressure.
And when that pressure is released to run the hydrogen fuel cell, it has another unique and absolutely necessary feature, a contamination filter. Hydrogen fuels are very sensitive to pollutants, such as ammonia gas and volatile organic vapors.
We decided we wanted something that would give a visual indication of when ammonia was starting to come through the tubing with the hydrogen. We came up with copper chloride, a chemical that starts off light turquoise colored and turns a very deep blue when it comes into contact with ammonia. We also, though, and this is where the fuse part of it comes in, we purposely chose the copper because when it reacts with ammonia, the crystals swell. And since this copper chloride is kept in a tube, it swells and shuts off the flow of any gas through it.
The result is a lightweight, rugged, practical source of pure hydrogen that can be used to power a wide range of consumer and industrial electrical appliances.
You want something that you can put in the trunk of your car or put in your backpack or keep it in your basement waiting for the lights to go out.
Hi, I'm Colonel Rob Friedel, the Chief Scientist of the United States Air Force Academy. If you're interested in licensing the technology you've heard about today, or pursuing other research collaboration opportunities with us, give me a call, 719-333-4195, and I'll put you in touch with the right people.